Okay, this is 7.2, number 5. And you can see we have two even functions here, y equals 2x squared and y equals x to the fourth minus 2x squared. All the exponents are even, so they're symmetrical to the y-axis. So rather than take the integral to find the area of the curves from -2 to 2, in which we'll have a little more computation, it's a lot easier to use symmetry and just take the area from 0 to 2 and double it. And that'll give us this complete area that they're talking about. So that's the approach we'll take. Now it's already set up for y equals, so it looks like it's going to be, y equals, so it looks like it's going to be in terms of x. And this would be my top curve, y equals 2x squared. This will be my bottom curve, y equals, this is the one that goes down like this, it curves around. Y equals x to the fourth minus 2x squared, that's my bottom curve. And then we're just going to use vertical rectangles. The width will be delta x, and the height will be this function minus that function. So we look over here, this is going to be the top curve over here, and this will be the bottom curve. This is the top curve here. So that's how we would set it up. The area would equal 2 times this integral from 0 to 2, top curve minus bottom curve. Pardon me. Okay. And x to the fourth minus 2x squared is the bottom curve. And we just have to integrate this so we can simplify it. And that's going to simplify to be, if I remove the brackets, I'll get 2x squared minus x to the fourth plus 2x squared dx. And that area will equal 2 times the integral from 0 to 2, and then we can combine these so we can have about 4x squared minus x to the fourth dx. And we just take our antiderivative, so we have 2 times, and the antiderivative of the 4x is going to be 4x would be 4x cubed over 3 minus, and that's going to be x to the fifth over 5, and again we're just going to evaluate that from 0 to 2 and double it. So that's going to be 2 times, if I put 2 in here, we're going to get 8, and 4 times 8 is 32, so that's going to be 32 over 3. Again, 2 cubed is 8, 4 times 8 is 32. And this is going to be 2 to the fifth. 2 times 2 times 2 times 2 times 2 is 32 over 5. Okay, so that will be the evaluation of 2 minus, and that's the nice thing, that's why we want to do the 0, because we get 0 minus 0. So we don't have to do any computations over there, so we just have 2. Put this up a little bit here. And we can put these all over a common denominator, so I can make this 160 over 15. Okay, minus 96 over 15. Multiply the top and the bottom by 5, top and the bottom by 3. So that ends up equaling, and it's going to be 64 times 2 is 128, so 128 over 15. That's your area. Okay. So again, using the symmetry makes it a lot easier. Okay, the next one. And I already did the sketches on these, so they'll be a little quicker. And now this is kind of in terms of y, but it looks like it's going to be a lot easier to do right curve minus left curve rather than top minus bottom, because it's going to be, we'd have to break it up into 2 integrals. It'd be kind of complicated. So what I did was I set it up like this, and you can see that this could be the right curve, this could be the left curve, and I would only have to use one integral. I wouldn't have to break it up. So the left curve was y equals x, so that's easy to change to x equals. That's just x equals y. The The right curve was y equals x squared over 4. Okay, so in order to solve that for x, I can just multiply both sides by 4, and then take the square root of both sides. The square root of 4 is 2, and the square root of y is y to the 1/2. So that's equal to x. So I set up over here like this. The integral from 0 to 1. So my rectangles would look like this. And again, their thickness is delta y, which becomes dy. And their length is the right curve minus the left curve. So that's how we get the area of these little rectangles that we're going to sum up from here all the way up to there. So there's my right curve minus the left curve. And then there's the width of all those little rectangles. Then we just have to evaluate that, which is pretty easy. We just take the antiderivative of this. So this is going to be 2 y to the 3/2. Add 1. Divide by 3/2 or times 2/3. 2 times. And then minus y squared over 2. And I'm just going to evaluate this from 0 to 1. And if I put 1 in here, I just have 4/3. Because 1 to the 3/2 is 1. So 2 times 2 is 4. So 4/3. Minus 1 squared is 1/1/2. Minus, and then when I put the 0 in, that's nice. That works out nicely because I just get 0 minus 0. And 4/3 minus 1/2, if I put those as a common denominator of 6, I get 8/6 minus 3/6, which is 5/6. That's your area. Then number 10. This was another one that it would look like it was set up to be, in terms of x, y equals x squared, x plus y equals 2. But I would have to do two integrals if I do it with respect to x, if I do vertical rectangles. So if I use horizontal rectangles and sum it up and integrate from 0 to 1, because I have that intersection point, it's pretty obvious right there. That's a point 1, 1. That'd be a little bit easier to do that, and I just use right curve minus left curve. So again, this is y equals x squared, so that's easy to solve for x. X equals y to the 1/2, or the square root of y. And if x plus y equals 2, that's even easier. X equals 2 minus y. So this is my right curve, this is my left curve. And like I said, I'll just sum these rectangles up like this. Like I said, the point of intersection is easy to verify. It's going to be 1, 1. Satisfy both equations. 1 plus 1 is 2. And the square root of 1 is 1. So that's going to be on both curves. So I set it up like this. Integral from 0 to 1 of the right curve, 2 minus y minus the left curve, y to the 1/2 dy. And we can simplify that a little bit. Well, actually, we could just remove the parentheses. And they're already set up, so I can already take my antiderivative right away. What's the antiderivative of 2 with respect to y? 2y minus y squared over 2 minus, and then y to the 3/2 over 3/2 or times 2/3. And I just have to evaluate that from 0 to 1. And when I put 1 in here, I get 2 minus 1/2 minus 2/3. And my other ones are all 0, so I get to do it like this, and I could put minus, and then, so those just drop out. And then I can put these all in common denominators, so I got 2, that would be, looks like my common denominator would be 6, so I got 12/6 minus 3/6 minus 4/6. And that's 12 minus 7 is 5, so 5/6. And that's your area. Oops, sorry about that. So again, 2 is 12/6, 3/6, 4/6, and these are all the zeros. Again, this is your f of b minus your f of a. Good old fundamental theorem, calculus part 2. The integral evaluation theorem. Okay, so 12/6, 3/6, 4/6, 5/6. Okay, hope that makes sense, and make sure you draw good sketches.